let's say I want to do the derivative of x to the 10th power. I could do the whole limit definition of a derivative where I do f of x plus h minus f of x all over h and take the limit as h approaches 0. Or I could use this really handy trick where I just bring the exponent, 10, down to the front and make the power one smaller. One smaller than 10 is 9. It works every time. If I want to do the derivative of x to the 8, I'd bring the 8 to the front and make the exponent one smaller. It doesn't even have to be an integer exponent. If I want to do the derivative of x to the 5.4, bring 5.4 to the front, make the exponent one smaller, so 4.4. This works for any n. This would be how you would write it kind of more formally, but you don't need this formal thing because maybe you probably understood what was on that previous page. This also comes in disguise in problems like this. Like this first problem is really asking the derivative with respect to x of x to the negative third power. By writing it as x to a power, that I know I can do, bring the power to a front, make the exponent one smaller. 1 less than negative 3 would be negative 4. This one is in disguise x to the 1/2 power. So I'll bring the exponent to the front, make the exponent one smaller. So it's 1 over 2 square root of x. This last one is really derivative of x to the 0 power, which makes it 0, x to the negative 1. It's 0. Just keep the derivative of any constant is 0. That kind of shows that it still follows the rule, but that feels like a bit much. So there's some other derivative properties that we can take advantage of. That the power rule was very useful. This is another very useful thing that you probably would guess even if I didn't tell you. It's that you're allowed to take constants out of a derivative. The derivative of c times f is c times the derivative of f. So in other words, the derivative of 2x to the 5th is 2 times the derivative of x to the 5th. It's 2 times 5x to the 4. I got 5x to the 4 using that power rule. So that makes it 10x to the 4. And I also kind of think about it as I do the exponent, I multiply to the coefficient in front. 2 times 5 is 10, and then I make the power one smaller. So this one I could make it 6 times the derivative of x to the 9, and I really don't need to show that stuff because in my head I'm thinking 6 times 9 is 54. X to the 1 power is going to, one smaller is going to be x to the 8th. Another derivative property that is very useful is the fact that derivatives distribute over addition and subtraction. That I can do derivative for this first one. I can do derivative of x to the 5 minus derivative of 2x cubed. Derivative of x to the 5 is 5x to the 4 using power rule. Minus derivative of 2x to the 3, I bring down the 3 and multiply it by 2 to make 6. And I make the power one smaller. I could do it over subtraction. I could also do it over addition. I'm thinking derivative of 4x to the negative 1 plus derivative of x to the 1/3 power plus derivative of negative 10. Or I could think about it as minus derivative of 10. Makes negative 4x to the negative 2 plus 1/3 x to the negative 2/3 minus 0. Derivative of constant is going to be 0. And I could write that in a kind of maybe more simplified way. I don't know if that's really more simplified. That takes care of x to a power, lots of properties, but there's other functions out there, right? Like what's the derivative of sine or cosine or e to the x? Well, I'm glad you asked. Derivative of sine is cosine. Derivative of cosine is negative sine. And derivative of e to the x, prepare yourself, this one you take some practice, is e to the x. It doesn't change. Derivative of e to the x stays e to the x. It's like impervious to derivatives. So we can practice. We can say, okay, derivative, if I had f of x equals that whole mess, maybe first I would rewrite f of x as f of x equals 5 cosine of x minus 3x to the negative 1/2 power plus 11. And I did that just so I could see the power on x, so that I can write f prime of x, the derivative of f, 5 cosine. Derivative of cosine is negative sine, so the derivative is going to be 5 times negative sine. This I use power rule, negative 3x to the negative 1/2. I do power rule, bring down the negative 1/2 and multiply it to the negative 3 to make plus 3/2. And then I make the power 1 smaller. Negative 1/2, 1 less than that would be negative 3/2. Derivative of plus 11 is derivative of constant is 0, so plus 0, or I don't even really need to write plus 0. For this one on the top right, my derivative of 3e to the x is going to be 3 times the derivative of e to the x, 3 times e to the x, minus derivative of x cubed, plus derivative of sine. The bottom left one. Maybe first I'll rewrite it, that way I can kind of see what kind of power I'm dealing with. Oh, that's to the 1/3 power, okay. Derivative of y prime, is going to be, I bring the power down, multiply it by 12, so 12 times a third is 4, and I make the power 1 smaller, plus 11 times 2 is 22, make the power 1 smaller, it becomes x to the first power. I'm not going to write that 1 in the exponent. Derivative of cosine is negative sine, so I'm going to have minus negative sine, which of course minus a negative, it's better if I just write plus. Not better, it's an opinion question. And this last one's here because it's a trick. You may be thinking, oh, I wonder if I could do derivative of x cubed times derivative of e to the x. No, you cannot. That's not a property I said. If you do it, I'll put you in math jail. You can distribute derivatives over addition or subtraction, but you cannot distribute a derivative over multiplication or division, over a product or a quotient. I promise I'll teach you how to take derivatives of products and quotients soon, but I also promise that in the meantime, if you try doing derivative of f times g by doing derivative of f times derivative of g, you're going to end up in math jail, and that'll just be sad. Good luck.